All right, so in this problem set, we're trying to predict the products, and the key to remember is you're starting with an ether, and you have to look at what reagent you have. And key thing to remember is if you have an acid that after deprotonation has a conjugate base that's a nucleophile, that's a decent nucleophile, then you're going to get an SN1 product like this. But if you have an acid with a non-nucleophilic conjugate base, then you're going to get an E1 product. Okay, so that's the key to remember: SN1, SN1, E1. Okay, so let's see how this plays out. So for this, even though the question does not require you to write out a mechanism, it's important to understand what happens to be able to predict the correct product. So the first step is protonation, and when that happens, I'll write it out on this side. That basically, I'll just condense the benzene ring and write it as pH. So there you go, you protonated it. And now the question is, well, is the bond going to break from here or here? And turns out if you break the bond here, you get a carbocation out here, which is more stable because of the aromatic ring. Okay, so we're going to break that bond. And that's the carbocation you generate. And on the other side, you have this alcohol, which is methanol. And then the Br minus, which is sitting aside, just goes and attacks that. So that gives you a pH CH2Br, and then the alcohol piece, which is methanol CH3OH. Okay, let's take a look at the next one. The next one out here, similar first step, the O gets protonated. That gives you, I'll write it up here, this kind of a species. And then again, bond is gonna break from here because it's gonna form a carbocation that can be stabilized by conjugation. So that's gonna give you, I'm sorry, this carbocation, and it's going to give you CH3CH2OH. And then the I minus comes and attacks that, giving you that. All right, now in this case, you're going to have an elimination take place. So the first step is still the same. So you're going to generate this species. Now the nucleophile is not going to attack because there isn't a nucleophile to attack. So I'm just going to copy this species over and write that here and show you what happens in the next step. So then you basically look for the beta hydrogen to the carbocation, and then that gets pulled off. What pulls that off? The conjugate base of this. Okay, you don't have to write it out. If you want, you could, but you don't have to. All right, and there you have it. Let's take a look at 3. Again, 3 out here is a little different. Still SN1 product, but now because you have two pieces that look very similar, you have to make a decision which one's going to grab the form the carbocation. So there you go. And that's going to make NO2 OH OH plus. Now, to remember which one forms the carbocation, you got to think about what this group does and what this group does. This group is an electron donating group and it's para to this position. So if you form a carbocation out here, the lone pair, the oxygen, is going to delocalize into the ring to stabilize that carbocation. Conversely, if you form a carbocation out here, which means if you break that bond, turns out that carbocation will get destabilized because the NO2 group withdraws electrons by negative resonance effect. Okay, so therefore, that is going to be my carbocation of choice, which means that's how the bond is going to break. That is going to give me this kind of alcohol plus that carbocation, and then the Br minus is going to attack this to give me that product. All right, and the last one out here, we have HI, and of course this is symmetrical, so it doesn't really matter which way you want to go. There you go, positively charged. Okay, and then what's going to happen is that's going to give me this kind of a cation. That bond is going to break. It doesn't matter, you can choose to break this bond, entirely your choice. Oops. And there's the carbocation, and then the I minus will attack that, giving you that as your product.